to talk about guns and bells. This is after the formulation. This is how you get it on the part in the first place before it goes to cure. And if you're selecting guns or bells based primarily on transfer function, you're missing half the picture, maybe more. So we're going to talk a little bit today about some interesting facts that maybe your suppliers don't tell you. And we're going to look at how they impact your choice and how these devices work in your coating process. And believe it or not, for you chemists out there, they really do have an impact on how you want to do your formulation. So we'll get going on that. Obviously, if we're laying down a coating, we're doing it for a reason. And the goal is always to get a continuous film on our product. And we do it for a number of reasons. We do it for beautification. We want to improve the aesthetic appeal of our product. We do it for protection, and it can be protection for a lot of things. It might be scratching, corrosion, UV damage, you name it. And we might do it to improve the performance of our product in its final application. That might be improving the resistance to moisture. That might be reducing drag, aerodynamic drag in the case of automobiles and airplanes and missiles and wind turbine blades. That might be hydraulic drag for boats, ships, submarines, torpedoes, that kind of thing. So there's a lot of reasons for doing it. There's a lot of ways to coat. You can brush it on. You can dip the product. You can flow coat. You can roll it on. What's pertinent to this particular conversation is spraying. Now, a spraying process is quite simple. We take our fluid, we put it through an atomizer, we create a cloud of very small droplets. We direct those at our product, the substrate as we call it. When the droplets hit the part, they recombine, they flow out, and they give us that film we're looking for. So far I haven't told you anything that you don't already know. The two primary ways of performing this atomization is guns and bells. Now, they both do the same job. You can expect that there's a lot of similarities. Both atomize the coating into a fan-shaped cloud. Both use compressed air to shape the cloud and to move it along. Both can be used in electrostatic applications. Now, if by chance there's someone out there that's not familiar with this, you charge the paint to a high potential, you ground the part, those little droplets take on that charge, and they're attracted to the part. And this is great because it reduces overspray and increases transfer efficiency. But if you can do that with both guns and bells, why are you using it as the criteria to make your selection? Doesn't make sense. There's got to be something else going on there, and in fact, there is. There's also a lot of differences. They both put out fan patterns, but as we can see, those fan patterns may be very, very different. And the reason that they're different is because of the different ways that guns and bells actually perform the atomization process. Other differences? Bells are traditionally larger and heavier than guns. This makes guns particularly attractive for manual operations where an operator is spraying a part. They're lighter, they're easier to control. And this leaves the bells primarily reserved for automated systems, robotic, reciprocators, things like that. All paint application equipment requires maintenance. Don't let anybody ever tell you different. But bells have a lot more moving parts. They're more complex. And therefore, they require more maintenance than guns. In general, there are exceptions. Bells are traditionally used with lower viscosity, low pressure materials. Whereas guns, while they can be used for the lower pressure, they're also able to handle higher viscosity, high pressure applications as well. All right, I said we'd get to atomization, and we're going to do that right now. Now, bell atomization is created by a rotating disc, and it generates shear in the material as the coating is pulled to the outside edge, and forces perpendicular to the fluid actually shear it apart. Because that's the definition of atomization. Shear a stream of fluid into teeny tiny little pieces and then just spray them all over the place. Now, when we look at this, our cloud is being formed perpendicular to the bell. And the atomization is determined by the cup design, shape, diameter, etc., the flow rate of the fluid being fed to it, and the speed of rotation, which determines the speed of that knife edge that's flying around there all the time. So the problem with this is the cloud is being formed perpendicular to the bell, but parallel to the part. This cloud will hover in space forever and never get to the part if you don't coax it along. So we coax it along with a shaping here. Get it over by the part, let the electrostatics take over and pull it in. And that's how bell atomization takes place. A gun's entirely different. With a gun system, we bring in the fluid, we reduce the diameter of the flow path, which increases the flow velocity. We then force it through a small orifice, and that causes shear in the system. The rate of atomization is determined by the size and shape of the orifice, the fluid flow rate through the orifice, and that's primarily determined by the pressure behind the fluid and the viscosity of the fluid as it's presented to the orifice. That's going to become important in a minute here. Like the bell, the fan pattern can be shaped with compressed air. The particles to the part to be drawn in by the electrostatics. What we can see here is a big difference in fundamental operation. And that big difference is because the fluid stream is already moving towards the part at a high velocity when it's atomized, guns create particles with higher velocity toward the part, toward the target, than do bells. That can be real important to your application. Now, we put this to the test in Carlisle Fluid Technologies lab in Toledo, Ohio. Just so happens they have a Malvern particle analyzer. Fantastic device. Uses a laser to measure the actual size of particles in the cloud and then report back what the general particle size distribution is. We did it, as you can see, with both a gun and a bell to compare performance, and we found some very interesting things. Now, to make it comparable, we had to have some test conditions, and they had to be consistent. So we used the same 2K clear code, and then to manage that, we used the Ransburg RCS system. It controls ratio, total fluid flow, and both atomizing and shaping air going out to the devices. Very important. Those have to be held constant, or the test means nothing. We used our temperature control system, which utilizes a recordable coax hose system. It's a new patented device that we brought out to work with coating systems, and it allows us to take temperature control all the way to the point of application, not back in the mix room where it starts. And that's a little bit different. Why would we do that? Well, it gave us the ability to control temperature as it was being dispensed. And I don't have to tell all you chemists out there, temperature and viscosity are kind of intrinsically linked. So, we used temperature to simulate ambient variations and their impact on coating viscosity so that we could look at that impact on overall atomization. The setup looks a little like this. You can see the ratio and flow control. We got a little temperature control unit. And then we've got this coaxial hose that runs all the way out to where the bell and gun are mounted, right next to the Malvern. So there isn't any distance in there to be impacted by any ambient variations that we might have. It's very important. We started with gun testing. Didn't really matter. Well-controlled system, all the parameters under control. We could have gone in any sequence, but we chose to test the gun first. We got results that we were expecting. We held all the parameters constant with the RCS, and then we used the temperature control system to make 10-degree steps from 65 to 115 degrees, and then we measured the resulting particle size with the Malvern. And what we're looking at here in particular is the dV50, which is the average particle size in the cloud. That becomes important in a minute. I said we saw what we expected. When the material is cold and the viscosity is high and we're moving through the gun, we produce an average particle size of about 52 microns at 65 degrees. But as we moved up in temperature and the viscosity fell, we saw that particle size fall to less than 39 microns. In other words, we got about a 30% change in atomization when all other factors were held constant, just because of the temperature-induced change in viscosity of the fluid. And that's because the flow through the orifice on the gun is a function of pressure and viscosity, and we're holding the pressure constant. Very important. So we would expect the same result with a bell, right? Not so quick. With a bell, our atomization is primarily mechanical. It's that knife edge going on out there, cutting our stream up into little pieces and parts. And so, even though we were holding the parameters constant with the RCS, and we did the same 10-degree steps, very carefully controlled at the point of application, when we measured the average particle size with the Malvern, what we found was that, independent of viscosity, we got about the same particle size in our cloud. That's kind of cool. And it's what everybody says. Oh, well, bells give you uniform atomization. But think about it. The material is still hitting the part at a different viscosity. So it's going to behave differently. So even though there was no change in atomization, the particles that we're putting out there are still very, very different at 65 degrees than they are at 115 degrees. We put them both on the same chart so that we can compare them. And we confirmed that atomization for the bell is primarily controlled by the rotation speed of the cup. And we did that by incrementing the cup speed from 32,000 RPM to 60,000. And lo and behold, what do you think happened? Average particle size dropped to about 16 microns. So, no great surprise in what we saw. Now, I mentioned the temperature and the particles when they get to the part. This is where things get interesting. There's this general belief out there that I have to control the temperature of my booth. It's extremely important because that determines the temperature of the particles of paint that are actually getting to my part. And we spend hundreds of thousands of dollars to make that happen. In automotive plants, it can be millions. On first blush, it makes a lot of sense because we're taking this stream of material, we're creating these teeny tiny particles and lots and lots and lots of them. That puts a lot of surface area in contact with the air. And so when we look at it, we think, well, they absolutely have to be at air temperature by the time they get from the gun to the part. Wrong. The reality is actually quite different. And this is where being a temperature control company comes in real handy. We can use a laser to measure the size of all of those little particles. But it can't tell us a damn thing about temperature. So, right now, the technology isn't out there to pick up the temperature of each of those little droplets. Doesn't matter. We're looking at the dV50, the average particle size. It's a simple heat exchange equation, simple thermodynamics, to determine what the actual temperature of the part is, of the particle is, when it gets to the part. We build models like this all the time, and these are done to help our clientele to better control and plan their processes. This one reveals a very interesting situation. We'll start with particle speed. We talked a little bit about this. Now, we said that gun speeds are higher than bell speeds. And in fact, Carlisle tells us that in their studies, they found that a bell will range between 150 and 300 millimeters per second in particle speed towards the part. Seems pretty good. A gun, on the other hand, will run from 300 to 600. Double the particle speed. Well, obviously, if I double my speed, my time to part is going to change significantly. And we can see that a gun will get you there in a half a second or so, whereas a bell can take upwards of a second and a half. But a second and a half is not a long time to affect a temperature change on a particle that's sitting in air. Remember, air is a very good insulator. It doesn't impart a lot of energy. And the particle itself is mostly plastic. I don't think I got to tell you that. So, basically, you don't get a lot of time to change. So let's look at this scenario. This is a typical scenario in a manufacturing plant. We're holding our booth temperature at a constant 25 degrees C. And I'll go one step farther. We're doing the same in our mix room. Good temperature control, we're holding them at 77 degrees Fahrenheit, and they're constant. We take our coating, and we pump it out of the mix room, we pump it up to the truss level in the building, we run it across the plant, and we drop it down into the booth to be distributed to our guts and bells. And when we do, it's a hot August day. We're air conditioning the snot out of our mix room and our booth, but we aren't worried about the air up there. So by the time the part gets to our booth, the paint gets to our booth, it's at 90 degrees. So now we're running it in, and we're atomizing it, and we're applying it to our part. And we're convinced that when it gets to the part, it's at 77 degrees. But in fact, when we look at it, that's not the case. The temperature change actually turns out to be very, very small. We can see that on a gun, we're only changing by 1/4 to 3/4 of a degree. We're always above 89 degrees when we get to the part. A little bit more predictable on the bell, we're changing there from 1 degree to a little less than 2.5. This paint that we are expecting to arrive at our part at a viscosity mandated by a 77-degree temperature is actually arriving at a much lower viscosity because it's actually more like 88 or 89. But if we're making our decisions and adjusting our processes based on the belief that we're at a viscosity correlating to 77 degrees, we're making some pretty bad decisions. And it's why we chase our tails when we're trying to get the parts right time after time. So, what does this mean for choosing a gun or a bell? Well, there's a lot of different factors that go in here. We've already established that guns are mostly used for manual applications because they're easier to hold on to. And we've determined that robotic applications work with both guns and bells. I mean, if you can mount a bell out there, you can easily mount a gun out there. So they're both applicable. This is done a lot. And let's look at a common application that I'm real familiar with. I'm from Detroit, and we paint cars all the time. And we use both. Well, why do we do it? Well, cutting. This is where you paint around the doors, where you paint inside the engine compartment, up inside around the dash, or maybe cutting in around the trunk. Deep draw areas where we need the velocity that comes from a gun to drive the paint into those deep areas. It's very important to understand that. But then when we get outside, we want those classy finishes on the hood, the trunk, the roof, the doors, the quarter panels. There we can use a bell. The consistent atomization is perfect for what we're trying to accomplish. So this extends to the first-tier suppliers as well. If they're forming parts like mirror housings or light housings, that kind of thing, they'll use guns to drive the paint down into those deep form areas. But if they're doing bumpers or fascia, they'll use a bell. Gentle curves, more susceptible or more compatible with lower velocity, let the electrostatics pull the particles in type of operations. So you begin to see how all these different factors play into the decision of selecting your atomizer. Easy conclusions to draw. Guns and bells both have their place. Big surprise there. Not that we're not taking sides. What we're saying is there's a purpose for both of them. And it's not uncommon to use them in combination, taking advantage of each of those strengths that we've talked about. But the key here is that neither style can overcome the problems created when the coating you deliver to them is not being held constant. You need everything to be consistent and constant if you're going to control your process. The goal has to be to pick the right atomizer for the job and then control the parameters of the coating, flow rate, viscosity, all of those things. When you supply it to the atomizer to assure that your process is both stable and predictable. And isn't that what we're really trying to achieve, both in formulation and in putting this on, so that we can cure it and sell the product to our end user? I want to thank you for being here this afternoon. I'm not used to such a big crowd in a house full of chemists, so that's really nice. I appreciate it. If there's any questions or anything else we can help with, there's lots more information than I know anything about on our website and at our blog. So please feel free to look there.